welcome to The Explainer. Okay, let's dive right into the incredibly fascinating theoretical framework known as Celominisignum. We're looking at this groundbreaking paper today that basically asks, how might unobservable information actually exist right here in our physical universe? It completely challenges our definition of what is real versus what is just, measurable.
I want you to really think about this opening question for a second. If our absolute best instruments can't measure something, does that mean it's practically gone? Well, in physics, we kind of often assume it is. But think about a radio station broadcasting a signal. Just because you drive out of range and your radio drops the music, does that mean the music literally ceased to exist? Obviously not, right? So today, we're going to explore how unobservable definitely does not necessarily mean non-existent. Here is our roadmap for today. We'll start with the radio station analogy, look at Hamilton's ordered pairs, dive into the Celominisignum hypothesis, climb the ladder of experiments, hunt for a universal coupling law, and finally wrap up with the mathematical challenge. All right, section 1, the radio station analogy. We're going to use a super straightforward, almost 6th grade level analogy just to understand how hidden information actually connects to our measurable world. Imagine turning a radio dial, or just adjusting the volume knob on a really weak signal. At first, nothing. You can't detect a thing. The coupling to your instrument is basically zero. Then, as you slightly improve that connection, you barely detect it, maybe just some faint static. A little more tuning, and boom, you recognize a pattern. And finally, you hear the music perfectly clearly. The absolutely crucial takeaway here is that the information itself didn't suddenly just pop into existence. It was literally always there. The only thing that changed was the strength of its connection, its coupling, to your observable reality. Moving right along to section 2, Hamilton's ordered pairs. Let's take a look at how mathematical history actually solved a remarkably similar problem almost 2 centuries ago. Okay, so before 1837, the square root of -1 was seen as this mysterious, almost fictitious thing. I mean, it was literally called imaginary. But Sir Rowan Hamilton took this super confusing abstract notation and made it totally intelligible by representing it relationally as an ordered pair. Fun fact, by the way, he was so excited by a related breakthrough that he famously carved the equations right into a stone bridge. He didn't make imaginary numbers real physical objects. Instead, he proved that the non-visible can participate rigorously in relationships that describe the physical world. And today, we literally couldn't do quantum mechanics or build electrical circuits without them. Which brings us perfectly to section 3, the Celominisignum hypothesis. Hamilton's work brilliantly sets up the historical foundation for applying this exact same relational logic to a brand new idea. So Celominisignum suggests that information may exist at tiny sub-Planck scales. We're talking scales infinitely smaller than anything our current physics could ever dream of measuring. But here's the catch. They don't exist as tiny, hidden physical objects. That's the trap we usually fall into. Instead, much like Hamilton's ordered pairs, they are purely relationships. They are informational states that are just insufficiently coupled to our ordinary reality for us to measure them. They only acquire conventional physical meaning through that coupling process. This brings us to the core observability equation. Observability, capital O, is a function of information, coupling, and scale. Just like turning up that radio volume, observability depends entirely on the underlying structure, the coupling strength, and your measurement scale. Meaning, below a certain coupling threshold, observability is practically zero. It just looks like random noise. But crucially, the underlying information is absolutely not zero. The information wasn't created as the coupling increased. Again, only its accessibility changed. All right, section 4, the ladder of experiments. Because let's be honest, an idea like this is really just philosophy unless we can actually test it in a lab. We need a progressive ladder of experiments. The source material actually outlines 6 proposed experiments to try and falsify the theory. And the real genius here? We can use systems we can actually control today, like optical modes, superconducting resonators, or electronic analogs. Rather than fruitlessly trying to build some impossible rulers smaller than the Planck length, physics already knows that quantum states can possess phase-space structures way below our observable resolution. So these experiments will specifically test if observable information systematically depends on the degree of coupling. Let's dive a bit deeper into experiment 4, the decoupling memory experiment, because honestly, this one could be a real game changer. In part 1, we take a highly ordered visible state, let's just call it state A. Then we deliberately and gradually decouple it from our measurement channel.
We dial down that metaphorical radio volume until its observable signature completely vanishes, becoming A prime. To our instruments, it is now statistically indistinguishable from random noise. Observability is essentially zero. But then, in part 2, we flip the script and reverse the coupling process. We reconnect it to see if the original information returns as A double prime, checking it with incredibly high fidelity. If that original information returns seamlessly, well, the experiment demonstrates a truly massive concept. A loss of observation does not equal a loss of underlying information. Unobservable simply does not mean non-existent. Section 5. A universal coupling law. If that decoupling memory experiment actually works, we move on to the strongest experimental test of all, the hunt for a cross-domain scaling law. In experiment 6, we would test completely different physical systems. We're talking optical interference states, electrical circuits, mechanical systems, quantum systems, even computationally simulated channels. And for every single one of these systems, we measure the exact same normalized quantities: the underlying information, the coupling strength, and the observability. We do this because we're looking for a dimensionless relation that survives changes of physical implementation. If these wildly different physical experiments repeatedly collapse onto the exact same mathematical curve, maybe something like a sigmoid curve with a common critical point, we wouldn't just have an interesting idea anymore. We would have hard, undeniable evidence for a scale-independent, universal coupling law that governs the accessibility of information in the entire universe. How cool is that? Which leads us to Section 6, the mathematical challenge. It's time to translate this beautiful, conceptual framework into an ultimate challenge for mathematical physicists. The source material issues a very explicit challenge here. Can you construct a non-trivial mathematical rule, a coupling operator, where information is strictly conserved while its observability changes depending on how strongly it's coupled to the measurable world? We need an equation proving this isn't just ordinary noise, standard quantum decoherence, or a silly glitch in detector sensitivity. Just as Hamilton gave mathematicians a rigorous way to represent the imaginary, Celominisignum challenges today's physicists to make the unobservable experimentally tractable. Ultimately, this leaves us with one profound question that turns all of this from a fun philosophical thought experiment into hard, falsifiable science. If we map out this mathematics, will our physical universe actually obey the proposed transformation? Because if it does, the things we currently write off as empty noise or completely non-existent might actually be the most richly ordered information in the universe, just waiting for us to find the right way to couple with it. Think about that the next time you look up at empty space. Thanks for joining me on this explainer, and keep questioning everything.